This is the 19th video in a series devoted to ordinary differential equations. In the previous video, we introduced the notion of the Laplace transform as well as the inverse Laplace transform. And we also built a little bit of a chart of Laplace transforms of certain functions and thus also the inverse Laplace transforms of the corresponding function. At the beginning of last video, I pointed out that the whole point of this was to have a new method for solving a differential equation by transforming it into an algebraic equation. And that's exactly what we're going to see today. But in order to do that, I need the following theorem, which we will prove. Okay, so let's look at what we have. So we'll suppose that f is a function from 0 to infinity to r. So in other words, the closed interval 0 to infinity. And we'll also suppose it's continuous and of exponential order. So I haven't defined what it means for a function to be of exponential order, but while we're proving this theorem, I'll point out what that means. Furthermore, let's assume that f prime is piecewise continuous. Then we have the following result, which relates the Laplace transform of the derivative and the Laplace transform of the original function. So the Laplace transform of f prime is equal to s times the Laplace transform of f minus f evaluated at 0. Furthermore, if we have like some nice conditions on f prime and f double prime, which I won't write here, but you can kind of guess what they are, we have the following result about the Laplace transform of the second derivative. So it's in fact equal to s squared times the Laplace transform of the original function minus s, the function evaluated at 0, minus f prime evaluated at 0. And you could probably guess that there's some nice formula that would allow us to find the Laplace transform of an arbitrary derivative. And in fact there is, and it's not too hard to get at, but we're not going to worry about it just yet. Okay, so the proof that we'll do here is really just computational with an arbitrary function f. So let's get to it. So we've got the Laplace transform of f prime is defined to be the integral from 0 to infinity, and then we have e to the minus st times f prime of t dt. So that's just the definition of the Laplace transform. And now we'll use integration by parts on this integral over here. And so, in fact, what we'll do is choose our u part to be e to the minus st. So that makes du equal to minus s e to the minus st dt by calculating the differential or taking the derivative. And then we'll take dv to be the rest. So this is f prime of t dt. That makes v equal to the function f of t. Okay, nice. Now we can use our formula for integrating parts. So this should be equal to u times v evaluated at the endpoints. So that'll give me e to the minus st times f of t. I need to evaluate that from 0 up to infinity. Notice that when I say evaluate it up to infinity, I really mean to take the limit. And in order for this limit to be nicely behaved, we need this e to the minus st to be the dominant term here. So that's what we mean by exponential order here. That means that when we take the limit as t approaches infinity of this object right here, we just get 0, meaning that's all that's left over is what we get when we evaluate at 0. But we're not quite there yet. Let's write out the rest of our integration by parts. So we have minus the integral from 0 to infinity of u or v du now. But notice this minus sign will cancel this minus sign. We have an s which we could pull out of this integral because this is a t integral. And then finally we have f of t e to the minus st dt. Okay, nice. So now by our previous discussion, we know this evaluated at infinity or limited as t approaches infinity will give us 0. That's essentially the definition of exponential order. So if we evaluate this at 0, we get minus f of 0 plus s times this integral, but this integral is exactly the Laplace transform of f of t by definition. So now if we look from here, to here, we've achieved exactly what we wanted to achieve, up to just reordering the stuff that's on the right-hand side. But I think that's okay. Okay, so now let's look at the second result, which involves the second derivative. So we've got the Laplace transform of the second derivative. Notice we can view that as the Laplace transform of the derivative of the first derivative, and then apply this rule. So applying this rule directly will give us minus f prime of 0, and then plus s, the Laplace transform of f prime of t. Again, all we've done is just replaced f with f prime in this purple underlined equation that we built. Now we can use this equation again, just with f replaced with itself. So that's going to give us minus f prime of 0 plus s, and then that Laplace transform will be minus f of 0 plus s times the Laplace transform of f of t. But then doing the appropriate expansion and then reordering some terms from this orange underlined stuff, you'll see that we grab this second equation. So that's good. Okay, so now let's use this Laplace transform along with the Laplace transform of derivatives in order to solve some differential equations. So of course, to start it off, we're going to solve the most classic differential equation, that differential equation which we solve with all of our new methods, which is y prime equals y. Okay, so the game here is that we will take this differential equation and we'll apply the Laplace transform to both sides of this differential equation. That will give us an algebraic equation. But before we do that, let's introduce the following notation, and this notation will be used over and over and over for these types of problems. And that is the Laplace transform of lowercase y, thought of as a function of t, is uppercase y, thought of as a function of s. Okay, that'll just help us out with a little bit of notation. Okay, so anyway, we need the Laplace transform of y prime is now equal to the Laplace transform of y. But now we can apply this rule over here, and what we'll end up with is s times the Laplace transform of y minus y evaluated at 0 equals the Laplace transform of y. And I wrote it as L of y instead of just capital Y, just for this first go around to make sure we know all where these parts come from. But now we'll make this replacement. So capital L of y, or the Laplace transform of little y, is capital Y. That gives me this nice equation, S times capital Y minus y evaluated at 0 is capital Y, which we can move around. So that's going to give us something like this. S minus 1 times capital Y equals y evaluated at 0. So that's from moving this capital Y over to the left-hand side of the equation and then adding the y of 0 to the right-hand side of the equation. Okay, so let's see. That gives us capital Y equals y evaluated at 0 over s minus 1. But let's recall that capital Y is the Laplace transform of little y, so that means little y is equal to little y evaluated at 0, and then the inverse Laplace transform of 1 over s minus 1. You might say, well, how did I take this little y evaluated at 0 out of the Laplace transform? But let's recall that this is just a number. This is the differential, or the solution to the differential equation evaluated at 0. So this is just a real number, and since it's a constant, we can pull it out of the Laplace transform and the inverse of the Laplace transform, given that those are both linear transformations. But now we go to our handy-dandy chart of Laplace transforms, which we built in the previous video, and we'll see that the inverse Laplace transform of 1 over s minus 1 is e to the t. I'll let you guys look that up if you need to, but that's what you get. So putting this all together, we have y is equal to y evaluated at 0 times e to the t, which is what we expect from all of the other methods of solving this differential equation. Okay, so let's do another. So our next example is another one that we know how to solve already, but I think those are good first examples just so that we can check our work. We have y double prime plus y equals 0. And then furthermore, we've got y evaluated at 0 as capital A and y prime evaluated at 0 as capital B. So those are our initial conditions. Notice they're somewhat general, but I think it's easier than keeping the y evaluated at 0 and the y prime evaluated at 0 into all of the equations. Okay, so let's get to it. We'll apply the Laplace transform to both sides. That leaves me with the Laplace transform of y double prime plus the Laplace transform of y equals 0. Again, the Laplace transform is a linear transformation. Any linear transformation applied to 0 gives us 0 from linear algebra class. And then we can split it up from addition, again, from linear algebra class. That's the definition of a linear transformation. Okay. So now we can apply the rules that we have over here. Let's set our notation up here. Capital Y is the Laplace transform of little y. Okay, so the Laplace transform of y double prime will be s squared times the Laplace transform of y, which is capital Y. And then we have minus s times y evaluated at 0, which is a, and then minus y prime evaluated at 0, which is b. So just to reiterate, this term right here expanded into these three terms right here based off the second part of our theorem as well as our notational setup up here. Okay, then we have one more term built into this, and this would be plus the Laplace transform of y, but by our notation that is capital Y. Then we'll want this to be equal to 0. Okay, so now we'll essentially just solve for capital Y. So what is that going to take? We'll have s squared plus 1 times y. That's from putting these together and then factoring out a common factor, which is the capital Y, equals s times a plus b. Okay, then we can divide by s squared plus 1. That gives us y equals a times s over s squared plus 1 plus b times 1 over s squared plus 1. Now we'll apply the inverse Laplace transform. Let's see, that will give us little y, because if you recall, by our notational setup, the inverse Laplace transform of capital Y is little y. Then we'll have a, the inverse Laplace transform of s over s squared plus 1. But again, you can look that up from the chart that we developed previously. That will be the cosine of t. And then we'll have b, the inverse Laplace transform of 1 over s squared plus 1, but that will be the sine of t. And so that gives us our final answer here, which is most definitely in line with what we would have expected from other methods of solving this differential equation. Okay, so that's good. Now let's do another one. For our next example, we'll look at the differential equation y double prime minus 7y prime plus 12y equals e to the 2t. We have an initial condition of y0 equals y prime 0, which equals 0. Okay, so we'll take the same kind of strategy that we did before. So we'll apply the Laplace transform to this whole thing. But notice that the fact that y of 0 is 0 and y prime of 0 is 0 means the Laplace transforms of the derivatives are quite a bit simpler here because we do not have this term or these two terms. So in fact, when we take the Laplace transform of y double prime, we'll get s squared times capital Y. From this right here, again, these two disappear. Okay. Then we'll have minus 7 times s times y for the same sort of reason, taking the Laplace transform of that y prime, and then plus 12 times capital Y, the Laplace transform of little y. Next, we need to take the Laplace transform of e to the 2t. If you recall, that's 1 over s minus 2 from some stuff that we did previously. Okay, nice. Now let's note that we can factor a y out of this left-hand side. That'll leave us with s squared minus 7s plus 12. Then we have this is 1 over s minus 2. Okay, so this thing factors. Actually, let's maybe do that in the margin. I think we have enough space. So this term factors as s minus 4 times s minus 3. I think that's pretty clear. So in the end, we'll have y equals 1 over s minus 2 times s minus 3 times s minus 4. So something like that. But we'd like to break that apart using partial fraction decomposition, and that's exactly what we'll do. So we need to set this equal to a over s minus 2 plus b over s minus 3 plus c over s minus 4. So that's the standard strategy for, breaking this apart. Now let's take this whole equation right here and we'll multiply it by that denominator, or the denominator product, I should say. So s minus 3, s minus 2, s minus 4. And then let's see what that'll leave us with. So we'll end up with a 1 on the left-hand side. And then next up, we'll have a times s minus 3 times s minus 4 plus b s minus 2 times s minus 4, and then plus c s minus 2 times s minus 3. So that's the stuff that does not cancel. And now we'll do the trick of evaluating this at some values of s that will simplify this quite a bit. So let's start by evaluating this at s equals 2, and let's see what that'll give us. So we'll have a 1 on the left-hand side of the equation. And then here we have 2 minus 3, 2 minus 4, so that gives us negative 1 times negative 2, which is positive 2 times a. So we have 2a there. Oh, but we're going to get 0 here because we have 2 minus 2. We'll get 0 here as well because we have 2 minus 2. So in the end, we'll have a is equal to 1/2. So let's maybe bring this a is equal to 1/2 up and just save it for the next step. Okay, so now let's move on to the next evaluation. Let's take s equal to 3 perhaps. So what is that going to leave us with? So the first term cancels. I guess I should start off with 1 is on the left-hand side. This first term cancels, this last term cancels. Then we have 3 minus 2, which is 1. And then we have 3 minus 4, which is negative 1. So that gives us negative b. So in the end, we have b equals negative 1. So we can replace this b with negative 1. Okay, now let's evaluate this finally at s equals 4 and see what we get from that. So here the first term cancels and the second term cancels. Then we get 4 minus 2 times 4 minus 3, that is 2. So we have 1 equals 2c. That tells me that c is equal to 1/2. I can bring that up here and I'll have c is equal to 1/2. So now what we'd like to do is notice that actually what we have is capital Y is this rational function right here that has been ripped into pieces using partial fraction decomposition, and it's set up perfectly to take the inverse Laplace transform. So let's do that. So if we take the inverse Laplace transform of capital Y, we get lowercase y, and then we'll have 1/2 e to the 2t from this term. The inverse Laplace transform of 1 over s minus 2 is e to the 2t. And then next we'll have minus 1 e to the 3t, and then plus 1/2 e to the 4t. Again, that's from doing standard inverse Laplace transforms that we saw from the chart that we built yesterday, or in the previous video, I should say. Okay, so let's maybe do one more. Okay, so here's our last example. We have the differential equation y double prime plus 2y prime plus 2y equals 1. Then we have initial conditions. Y evaluated at 0 is -3, and y prime evaluated at 0 is 1. Okay, so we're using the Laplace transform here, just like our previous examples. So let's see what happens to this if we take the Laplace transform. So this first term will become s squared and then capital Y. Again, we're using the same notation, capital Y is the Laplace transform of little y. But in this case, we have to do something with the initial conditions. So what will those give us? So next up, we'll have minus s times f of 0, but that'll give us plus 3 times s because the minus sign cancels. So that's from that part. And then we'll have minus 1. That'll be from this part right here, from this part of this formula. Okay, So just to reiterate, that's what happened to our y double prime. And then we'll have plus 2 times what's happening to y prime, which will be s times capital Y, and then minus our initial condition f0. So that'll be plus 3 in this case because the sign changes. And then we have plus 2 times the Laplace transform of y, so that'll be 2 capital Y equals. Now we need to take the Laplace transform of the number 1. Let's recall that that is 1 over s. From, again, some stuff that we did last time. Okay, so now we're going to start putting some things together. So I'll start by collecting all of my capital Y terms. So let's check it out. I've got an s squared times capital Y here, a 2s times capital Y here, and a 2 times capital Y here. So putting that all together, I have s squared plus 2s plus 2 times capital Y. Then what else do I have? Well, I have this plus 3s, and then I have 3 plus 2, which is 6, minus 1, which is 5. So I can actually move all of that to the other side of the equation, and that'll give me 1 over s minus 3s minus 5. So again, that's from moving that to the other side of the equation. Okay, great. Now we'll divide by this s squared plus 2s plus 1, and that'll leave me with y equals 1 over s times s squared plus 2s plus 2, I should say, and then minus 3 times s over s squared plus 2s plus 2. Maybe I'll write it like that, just kind of looking ahead towards the inverse Laplace transform. And then finally we'll have minus 5 and then 1 over s squared plus s plus 2s plus 2. Okay, good. Now let's take a look at this first term and notice that we need to do some work on this first term. We don't need to do any work on those second two terms because if you recall the chart from last time, along with some shifting rules and some completing the square in the denominator, which we will get to, we could take the inverse Laplace transform of those. Okay, so we need to do a partial fraction decomposition on this pink underlined term. So that means we'll take 1 over s times s squared plus 2s plus 2, and we'll split it up as a over s plus bs plus c over s squared plus 2s plus 2. Again, we've got that irreducible quadratic. Now what we'll do is take this entire thing and we'll multiply that by that denominator in order to clear this denominator out. That'll leave us with the following equation. We'll have a times s squared plus 2s plus 2 from the a times that with the s canceling, and then we'll have plus bs squared plus cs. Again, the irreducible quadratic cancels here, and I distributed the s through, and then I have this is equal to the number 1. That's from this left-hand side. And now we can extract appropriate coefficients. We'll extract our constant term, we'll extract our s term, and we'll also extract our s squared term. One at a time, that should build a system of equations that we can solve. Let's start with our constant term. On the left, there's only a single constant term, which we get from a times 2, so that's 2a. On the right, there's just the number 1. So that means a is equal to 1/2. So that means we've got a value for our a to start with. Okay, so maybe we could input that in here if we wanted to. This is 1/2. Now let's see what we get for our s term. So here we have 2a here from this 2s times a, and then we'll also have plus c, and this has to be equal to 0. And that's because we don't have any s's over there on the right-hand side. So since we know 2a is 1 from this equation, we know that c is equal to -1. So now we have our second value. So that means we can take this c and replace it with -1. So that's pretty nice. And then finally, we can look at the s squared terms. And here we have a plus b on the right-hand side, or the left-hand side, and 0 on the right-hand side. That means b is equal to -a. That means b is equal to -1/2. So that means we can take this b and replace it with -1/2. Okay, so now let's take this expression and slide it in right here, and then we'll start combining like terms. So this is where we left ourselves off. I factored some constants out and moved some things around. I put that 1 over s term way over there, but that comes from our previous step. Now we're ready to combine like terms if possible. Notice that this underlined term and this underlined term in orange are like terms. They're both of the form s over s squared plus 2s plus 1. And then furthermore, this red underlined term and also this red underlined term can be combined as well. And then looking ahead, we'll probably want to complete the square on this irreducible quadratic in the denominator. So I'll just say that we can write this s squared plus 2s plus 2 as s plus 1 quantity squared plus 1. Okay, so now let's start putting some stuff together. So we'll have negative 7 over 2, and then s over s plus 1 quantity squared plus 1. Okay, that's good. And then we'll have, let's see, minus 6, and then 1 over s plus 1 quantity squared plus 1. And then finally plus a half, 1 over s. Okay, now we're actually almost done, but not quite done. We can take the inverse Laplace transform of this term right here and this term right here very easily, but we can't do the inverse Laplace transform of this first term very easily just yet, and that's because this has an s plus 1 quantity squared in the denominator, which means this should have an s plus 1 in the numerator. So if we put an s plus 1 in the numerator, then what we've actually done is subtracted 7 halves. But if I've subtracted 7 halves, what I need to do is add 7 halves to this side. But this is 12 halves plus 7 halves, or negative 12 halves plus 7 halves gives me negative 5 over 2. So that finishes everything off until it's to the point where we can just look it up. So now we'll apply the inverse Laplace transform. We'll get negative 7 halves. This is equal to e to the t cosine of t, by that shifting rule I talked about. And then here we'll have minus 5 halves e to the t sine t, again by that shifting rule. And then plus 1/2 and just 1/2, because the Laplace transform of 1/2 is 1 over s. So we're good to go with that. So putting this all together, we have our final solution down here. Okay, good. So now I'll leave you with some warm-ups. So I've got 2 warm-ups to start practicing this material. So the first is the differential equation y double prime minus y prime minus 6y equals 2t. We've got initial conditions, y evaluated at 0 is 1 and y prime evaluated at 0 is 0. Then we have the following differential equation, y double prime plus 4y equals 3 sine t. And then we have y evaluated at 0 is 1 and y prime evaluated at 0 is negative 1. And that's a good place to stop.